Okay, welcome everyone. Let me introduce today's speaker. It's Tomáš Bučko. He's an associate professor at the University of Bratislava, and he's been contributing towards VASP for almost 2 decades. His scientific interest lies chiefly in catalysis, and as a consequence, he's really become pioneer of all the molecular dynamics features in VASP. It's fantastic to see that all these advanced MD features now get to shine after they became so much more computationally more feasible with machine learned force fields. Excited to hear about modeling chemical reactions and advanced MD methods in general from you today, Thomas. The title of the talk, of course, is Static Approach to Reaction Kinetics. So, Thomas, we're all ears.
Thank you very much, Chris. Hello, everyone. Welcome to first of my talks about exploring chemical reactions in VASP. So this is the outline of today's lecture. I will start by reviewing theoretical background, basic theoretical concepts that we will need. Then I will introduce a demonstration reaction that I will need for demonstration purposes to show you how things work. Then we will move on the main subject of today's talk, and that's the static approach to chemical kinetics. We will introduce basic assumptions and approximations that are made within this approach. Then I will talk about the workflow that I'm using in my static calculations. Those that involves initial transition state, gas, preparation, vibration analysis, its relaxation, intrinsic reaction coordinate following, and thermodynamics calculations. I will very much focus on practical aspects of the calculations, and therefore I will talk also about one common problem with thermodynamic calculations of static approach, which is due to incorrectness of vibrational spectra. So I will address this problem. I will show you what to do in this case. And in the end of my talk, I will talk a little bit about limitations of static approach. Then next subject is molecular dynamics approach to chemical kinetics. And that's basically the topic we reserve for my next lecture within this workshop. Before I move on, I would like to mention that I prepared a document, a PDF file called Investigating Chemical Reactions with VASP, a practical guide, which will be available for you for free. Let's start with theoretical background. Let's consider elementary transformation between two stable states, R, reactant, and P, product. Now, reaction rate is defined as time change of concentration of product, and it can be expressed like that. Now, CR and CP, these are concentrations of reactant and product, and K, R to P, and K, P to R, these are rate constants for the forward and the reverse reactions. Now, assuming that no other product is formed in the reaction, it's just a reactant and product that are involved. So then the sum of their concentrations must be constant. And therefore, the time derivative of concentration of reactant is minus that of concentration of product. So using this equation, we can easily also express time derivative of concentration of reactant. In the limit of infinite time, the equilibrium should be established. So the concentrations of reactant and product should not change anymore. So the relative concentration of those two should be constant. This constant has a name, that's equilibrium constant. And of course, if concentrations are constant, that also means that the reaction rate must vanish. So put 0 on the left-hand side of this equation, separate Cp over Cr, and you see that equilibrium constant can equivalently be expressed as ratio between forward and reverse rate constants. Now, we see from this theoretical introduction that in order to access chemical kinetics, we basically need rate constants. Now, rate constants are phenomenological quantities. They can be measured by monitoring concentration of reactant or product over time, but how can we access this quantity via computer simulations? Clearly, we need theory that links micro and macroscopic quantities. So we need to use machinery of statistical mechanics. Throughout this workshop, I'm going to use semi-classical NVT or canonical ensemble. It's called NVT. This means fixed number of particles and volume V and temperature T. Now the partition function has this form Q that stands for 3-dimensional vector of atomic positions. I'm using Cartesian coordinates. P are associated momenta. H is Hamiltonian, which is just the sum of potential energy and kinetic energy. And Cn here, that's normalization constant. The exact value is not relevant for our purposes. Within this ensemble, observables can be expressed as ensemble averages. Yeah, so here we have partition function, and this is phase space function associated with the property of interest, O. Not every physical property can be expressed in this form. A prominent example is Helmholtz free energy, which is defined as minus kBt logarithm of partition function. Now, for our purposes, it will be useful to introduce dependence of Helmholtz free energy on some geometric parameter, call it psi. Okay, so if we introduce this dependence on the left-hand side, we have to do the same also on the right-hand side of equation. And here, Q of psi, that's the canonical partition function for a special ensemble of configuration with a fixed value of psi. Okay, so out of all configurations there are, we select only those for which this function takes this particular value. Okay, now this quantity is related to probability density of psi. First, probability density is expressible as observable in this form, and the corresponding phase space function linked with this property is just the delta function. Okay, so we can directly use this prescription to express this property, and we arrive at this formula here. And now comparing these two equations, we see that probability density can be expressed in this form. It is also useful to express free energy difference between two states linked via a continuous reversible path. Again, call it psi. Okay, so imagine we want to compute difference in free energy between two states with fixed value of psi. This is, by the way, nothing but reversible work needed to shift value of psi from value 1 to the value of 2. Now, using this definition and combining it with these two formulae, it's easy to show that this difference can be expressed in terms of probability density. One last thing that we need to introduce is the conditional average for the property O for ensemble of configurations with fixed value of psi. Okay, so again, out of all configurations there are, we select those for which psi takes some specific value, and only for those configurations we evaluate the quantity of interest, O. So this is the conditional average. And it is easy to show that the relation between the total averages and the conditional averages, so this relation is like that, where probability density appears on the right-hand side of this equation. Suppose now that the reversible transformation, the reaction between R and P, can be realized under the canonical NVT conditions simply by varying the value of psi. Let's call it the reaction coordinate. And let's choose psi in such a way that reactant configurations has value of psi smaller than certain preselected value, psi asterisk. Okay, so everything to the left from this line, these are reactant state, and everything to the right corresponds to the product state. Okay, so we can choose this special value of psi asterisk that allows us to distinguish between R and P. We can select it to be on top of a free energy profile. This is free energy as a function of psi, and we can select a value of psi asterisk to be this particular point. Now for this setting, using fluctuation dissipation theorem, Bennett and Chandler derived the following equation for rate constant. To make explanation of terms easier, I arrange it into the following form. I just introduce to numerator and denominator the same term and split it into two parts. Now, what you see here, this is Heaviside step function. That's 1 when its argument is negative and it is 1 otherwise. So at which circumstances is this argument negative? So this is when psi is smaller than psi asterisk. So this is when we are sampling reactant configuration. So all this term can be interpreted or is related to partition function of reactant configurations. The term in a numerator, this is probability density for transition state. And combining these two things together, this is probability density of transition state among all reactant configurations. Okay, so this is quite simple interpretation. Now, when we look at the other term, we see that it has a form of conditional average. So we have the delta function here and here, and it's ensemble average of what? So we have initial velocity here of reaction coordinate, and then we have here Heaviside step function that selects values of psi determined for some time later after 0. Okay, and the contribution of this term is non-vanishing only if value of this psi of t is greater than psi asterisk. Okay, so in plain words, this term can be computed by first obtaining ensemble of transition state configurations. Okay, and then for this ensemble, we generate randomly initial velocities. Okay, and then from these initial conditions, we propagate system in time. Okay, and now at every moment we can determine value of psi. And when we are on the product side, the contribution to average will be initial velocity. When we are on reactant side, then the contribution would be just 0. As you can see, Bennett-Chandler rate constant is time dependent. Now, this is elegant and in principle exact semi-classical theory, but unfortunately, it is quite time-consuming. It's prohibitively too time-consuming in the context of ab initio computer simulation. Okay, so that's why we need to make some further assumptions, some further approximations to make the calculations of rate constant feasible. In the context of ab initio computer simulation, it's transition state theory, which is almost exclusively used. So unlike Bennett-Chandler theory, transition state theory assumes no transition state recrossings. That means within transition state theory, we only consider trajectories which start in reactant. And once they pass through transition state, they necessarily continue towards product. And events like this, like the red line here, that we start in reactant, cross transition state, but then recross it towards reactant again. So something like that doesn't exist within transition state theory. This is neglected. Transition state theory can be elegantly formulated as a time 0 limit of the Bennett-Chandler theory. If you do the exercise, we arrive at this formula. So here we have Heaviside step function for the initial velocity, and we don't need to evaluate system in time, as you can see. So this rate constant is time independent, unlike its Bennett-Chandler counterpart. So look at how elegantly this formula implements the basic assumption of transition state theory, no transition state recrossing. You see, so this ensemble average is done over transition state configurations. Okay, we generate initial velocities, and if they are positive, that means that the arrow leads towards product state. Okay, so then we assume that such trajectory will inevitably end up in the product. Okay, otherwise there will be recrossing, which is not allowed within transition state theory. Clearly, transition state theory overestimates through rate constants. In fact, we can introduce correction transmission coefficient. It's correction factor that corrects for missing dynamical effects within transition state theory, such as trajectory recrossing, and formally it can be defined as Bennett-Chandler theory rate constant over transition state theory rate constant. Now, so let's stick with transition state theory and let's work out the equation we obtained as a 0 time limit of Bennett-Chandler formula. We can rearrange it as follows, where the individual terms have very clear meaning and can be quite easily accessed via computer simulation. So the first term here, this is conditional average of absolute value of velocity linked with reaction coordinate at transition state. The last term here, that's probability density of arbitrarily chosen reference reactant state. And the central term here, that's exponential term, which has in exponent reversible work needed to shift the value of reaction coordinate from this arbitrarily chosen reference reactant state to transition state. I emphasize again, this state, this reference reactant state can be arbitrarily chosen. That's obvious from the form you see here. We have the same term in numerator and denominator. So whatever change you make here, you also do here. So whatever change you introduce by changing your reference state here is reflected also in this term, and it exactly compensates. So you can choose this state at your will. Now let us compare this equation with equivalent equation, Eyring-Polanyi equation, which also describes rate constant within transitional state theory. It has this form here. In addition to physical constants and temperature, we have here the quantity which is called activation free energy. Okay, so now equating these two, the formula, so we can single out, we can separate activation free energy, and we arrive at this form. And you see that despite, so popular of explanations, free energy of activation is not just the difference in free energy between the top of the barrier and bottom of a valley of reactant. It's more because it contains also contributions from velocity in transition state and probability density in reactant. Now, within Eyring-Polanyi theory or transition state theory formulation, you see that having access to free energy of activation, you can immediately compute rate constants. Free energy is just more convenient to work with in computer simulation. It's energy, so it's a more convenient quantity for us to work with. So let us focus on calculation of this quantity. For demonstration purposes, I selected reaction in red. This is the rate determining step for whole sequence of transformations of syngas into something more useful. Syngas, that's a mixture of hydrogen and carbon monoxide. This sequence of reactions is catalyzed by zeolite. And the reaction in red is the rate determining step for this sequence, meaning that this is the slowest reaction step from this sequence. This is the reactant for reaction. Here, carbon monoxide weakly interacts with methoxy group formed in zeolite. Okay, and in the product, we create acetyl cation, okay, which is just inside zeolite cavity. As a zeolite catalyst for our test purposes, I selected shabazite. It has nice property that its primitive cell is quite small. For this model, we only need unit cell with 42 atoms, including a reactant molecule. In my simulations, I set mass of all hydrogen atoms to 3 atomic mass units. The results that I will show you today and also in my next lecture were produced using PB plus D2 functional. So within the hands-on session, you will see machine learned force fields trained on PB plus D2. So that will be the reason why my results and the results that you obtain on hands-on session will be slightly different. Based on experiment, I selected temperature of 440 K in all my simulations. Now let's move on. Our main subject, that's a static approach. Let us first summarize the assumptions and approximations that are made within this approach. So the basic object we will work with is potential energy surface. This is normal, it's hypersurface that depends on 3 degrees of freedom. That's something that is not easy to visualize. So I have here only a model surface that depends on 2 degrees of freedom. Now, within this static approach, we assume that there is only one minimum representing each of the stable states. Okay, so the macro state, this is sum of micro state from certain valley on this potential energy surface. And the special point is the minimum, which is meant with geometry that is meant to be representative of the entire stable state. And the same also for other stable states. So for other stable state, we have another minimum, another valley, okay, another basin, and the corresponding minimum is representative of that state, and the same for perhaps for some reaction intermediate. Now the transition state, that's dividing surface between 2 stable regions. Okay, so in 2 dimensions, it would be just the line that simultaneously belongs to R and P, for instance, right? And again, there is a special point here, which the highest Boltzmann weight. This is the structure with the lowest energy on the line, and that's minimum on the line, and that's basically first order saddle point on full topology, right? This is again something that we will simply call transition state, even though full transition state, in fact, is basically manifold of all these configurations here. One more important thing, it is also assumed that transition state can be reached by exciting one specific vibrational mode of reactant. Now, within static approach, within this approximation, each degree of freedom of a stable or transition state can be uniquely classified as electronic, vibrational, rotational, or translational. And these types of degrees of freedom are assumed to be fully decoupled, so we can express the partition function as product. Having a partition function in this form, then it's easy to see that free energy then must be simply sum of contributions. Now, for different degrees of freedom, for vibrational, rotational, and translational, we use different models, specifically harmonic oscillators, rigid rotor, and ideal gas models. This is my basic workflow that I use in my calculations. I always start from transition state, and this is what I recommend to you too. So I start first preparing some initial gas for my structure and perform vibrational analysis to prepare a setup for my transition state relaxation. I relax, perform vibrational analysis again, and confirm that a vibrational spectrum is correct. If this is not the case, I take some measures to correct the spectrum. Then I follow intrinsic reaction coordinates to identify these stable states linked with that transition state. Next, if needed, I find relax, what I find in the step 4, and perform vibrational analysis for that. And finally, I use the data accumulated in previous steps, energies, geometries, and harmonic frequencies to determine free energies of reactant and transition state. And from the difference between the two, I compute activation free energy. Yeah, so first step in my workflow is to prepare initial transition state gas structure. This is usually not very difficult if you know or have at least some idea of the structure of reactant and product. Okay, so what you can reasonably expect is that transition state will be just something with geometry in between reactant and transition state. Here, of course, some basic chemical knowledge and intuition is useful. So in our demo reaction, in reactant, we have methyl group attached to oxygen and only loosely interacting with carbon of carbon monoxide. In product, this bond is broken and this bond is created. So we can expect that, yeah, methyl group is moving. So in transition state, methyl group should be somewhere in between. Moreover, methyl group in reactant has this approximately tetrahedral structure. It has tetrahedral structure also in the product, but it's oriented differently. So clearly, flipping of CH3 pyramid must be a part of reaction. So again, in transition state, we expect to be somewhere in the middle of this flipping. So we can reasonably expect that in transition state, CH3 will assume approximately flat configuration. So based on these ideas, I constructed this structure. This is my transition state gas. And the distances R1 and R2, I just deliberately set them equal to a 2.1 angstrom. Now about relaxation, yeah, so minimization, relaxation of potential energy minima, that's easy. Okay, so even simple force following algorithms would do the job. Yeah, so all we can do is just follow direction of forces, and little by little we approach the minimum. Maximization is not much more difficult than that, because we only need to follow direction opposite to forces. We do almost the same thing, but in opposite way. Okay, so in some sense, we can look at maximization as we can think of it as of minimization on the inverted surface with forces with negative sign, with opposite sign, right? Now, the first order saddle point optimization is much more complicated than minimization and maximization. And that's because we need to maximize along one specific direction and minimize along all other degrees of freedom. And this special degree of freedom along which we will maximize is not known a priori. This is the reason why the transition state optimization algorithms require besides the initial structure, also the guess for unstable direction. I will call it U of psi as input. So in some trivial cases, you can guess this, for instance, of surface diffusion along certain high symmetry axis, then of course it's not very difficult to guess it. But in general case, you have to determine it somehow differently. And we will see how. Now, VASP has two different algorithms for transition state relaxation. The first one is called Nugget Elastic Band Method, or NEB. And in this algorithm, multiple configurations distributed along path, or transformation path, defined by or guessed by user at the beginning of relaxation. So multiple images are distributed along this path. Optionally, they are connected via harmonic springs, and whole this object is then simultaneously relaxed. Okay, so what we do, in fact, so for each image, okay, so we imagine this is connected to form this kind of string, and locally for each point, for each image, we can determine the unstable direction as tangent to such string, right? And now, depending on the particular setting, we remove component of force parallel with unstable direction. And yeah, depending on particular setting, we can replace it by spring forces, okay? And then just perform usual relaxation step. This would bring us to new positions, defining a new kind of string, and this is cycled over and over. From what is said, it's clear that the more images, the better representation of this object, okay? And therefore the better accuracy or better chance to have successful relaxation. But at the same time, since all these calculations are done in parallel, okay, so your CPU power is distributed among images. So of course, the more images you use, the more expensive the calculation is, right? Besides that, there is one more reason why I don't prefer to use this method in my calculations. The other reason why this is the case is that defining initial positions for images might be pretty difficult in some cases. When atoms do not move on simple straight lines, but rather they follow some complicated curvilinear motion. So let me show you examples. So think of this reaction, for instance. So in this reaction, so this reactant is moved and reoriented a little bit, then proton transfer takes place, carbon atoms are reconnected, another proton transfer, and then rotation back. And this is just one single reaction step with one single transition state, okay? Honestly, I would not be able to prepare the initial path with small number of images. It would be very difficult for me to guess what exactly will happen during reaction. So this is the reason why I prefer to use in my calculations the other method that we have in VASP. This is called improved dimer method, or IDM. The word dimer here is because the basic object that it uses is a dimer constructed in 3n-dimensional configuration space. This dimer consists of point Q, that's structure that is initially provided by user, and Q shifted along unstable vector by some small step, delta. The size of this step typically is something like 0.01, 0.02, something that you also use in vibrational analysis when you use finite differences, of course. Now, the algorithm in its simplest version, in its default setup, works in 4 cycles. Okay, so one relaxation step consists of 4 SCF forces calculations. Okay, so in the first step, we compute forces for the given point. In the next step, we compute it for another point, for the other point of the dimer. From this information, we can now compute curvature along unstable direction. Then we perform a trial rotation of dimer by some trial angle phi1. From that information, we can compute curvature linked with rotation and estimate the optimal orientation of dimer that maximizes the negative curvature along unstable direction. So we rotate dimer in such a way. Okay, so this was initial orientation. Now we reorient it in this way. Okay, and now we revert direction of forces parallel with unstable direction. So formally we do this. Okay, and now we define surge direction that is parallel with these forces, and that would be surge direction, and perform small trial step along this surge direction. From that, we determine curvature for the motion along trial direction. And from that, we have enough information to guess position of minimum along search direction. And that new Q is a new configuration used for new step I, okay? And the whole cycle is then repeated, okay? So it's important to remember that Daimer method works in 4-step cycle, so to say. As already mentioned, so in addition to initial structure, we have to provide in the postcard file also information about the unstable direction, or we can call it trial Daimer axis. So now how to determine that, how to make the guess for that. So for this, it's useful to perform vibrational analysis and estimate this unstable vector as a Hesse matrix eigenvector with negative force constant, which is approximately parallel with the expected motion of atoms during the transformation. Yeah, this slide says a little bit about the vibrational analysis. So in that we compute harmonic frequencies from the eigenvalues of what is called dynamical matrix. This is 3n by 3n square matrix with elements like that. Mi, mj, these are atomic masses for degrees of freedom I and j. And h, ij, that's a component of Hesse matrix. That's again 3n by 3n matrix of second derivatives of potential energy. If you use finite differences, that's Ibrion 5 algorithm implemented in VASP, then the element of Hesse matrix is computed from forces via finite differences. We can diagonalize Hesse matrix and its eigenvalues. These are force constants, and its eigenvectors can be used, for instance, to estimate the initial unstable direction for Daimer method. So this is what we want to do. Now, the eigenvalues, eigenvectors of Hesse matrix are normally not written in the output files generated by VASP when you perform vibrational analysis. Nevertheless, the outcar file, the resulting of outcar file, has all the information that we need to reconstruct Hesse matrix. So this is the purpose of program VIPFREG. It just reads outcar and perform and reconstruct Hesse matrix. So on the way, it also computes vibrational frequencies. Now I apply that, I use it for my trial transition state structure, and I see I have 4 imaginary frequencies. So I have 4 candidates for suitable guess for unstable direction. Now, which one should I choose? Which one should I choose? So 4 imaginary frequencies also means that the Hesse matrix must have 4 negative force constants, and I can use the output file Hesse modes Molden generated by VIPFREG to visualize individual vibrational modes and simply decide which one best fits my proposal. So let's click through that. So this is the first vibrational mode. This is obviously something soft, which couples lattice vibration. Doesn't look like a reaction. The other mode is quite similar. No, it's not that. The next mode, this is clearly just internal rotation of methyl group. No. And the final bingo, this is it. So here we see a reconnection of methyl group between oxygen and carbon. This is very similar to what should happen in our reaction. So clearly the Hesse matrix eigenvector with eigenvalue with force constant of -11 point something, that's the right one. Now, VIPFREG also generates other file Hesse modes .dat, where force constants and corresponding lattice vectors are listed. So this is the format for force constant, eigenvector, separating blank line, another force constant, corresponding lattice, corresponding eigenvector, etc. So now we remember the vibration that we were interested in is -11.6. That's right, the first one. So what we need to do is take 3n lines corresponding to the eigenvector and copy paste them to the postcard file right after the area where positions are defined. Okay, so here we have blank separating line, and after that, at this place, unstable direction should be defined. That's the postcard file. Then we need to define Ibrion 44 in car file. By that, we tell VASP that we wish to run Daimer method calculation. We also need to specify our relaxation criterion as usual using edif G. this is the criterion I'm using. Negative sign means that the forces acting on atoms must be smaller than this value, 0.005 eV per angstrom. This is relatively strict relaxation criterion. There are more flags that control behavior of improved dimer method. Normally, you don't have to touch them, but if you are interested, if you know exactly what you are doing, so you can visit, so you can check documentation. Now, suppose the simulation is running. Transition state relaxations are always tricky. Yeah, so there are many ways that can go wrong. So I strongly recommend to regularly check the relaxation. There are many things that can go wrong. So one useful diagnostics is to check curvature along unstable vector that is seen by the optimizer. Okay, so this can be easily accessed. So this information is written in outcar file. You can simply grab curvature or simply look up that string. And what you should see is just sequence of negative numbers. That means that everything goes well. On the other hand, a long sequence of positive numbers usually means that the algorithm failed to converge, and you should better restart the simulation, for instance, from different initial structure. Of course, as in any other relaxation, the gradients should decrease in the course of simulation. Now we should remember that that one single step of improved dimer method involves 4 SCF calculations. Okay, so the information of gradient is written in the outcar file. You can, for instance, grab for max gradient, and now you see that only a first of every 4 values really changes significantly, right? So that's because only in the first step, really the optimization step was performed, and in the rest of the cycle, so trial rotations and trial movements are performed. Okay, so this is important to keep that in mind. But nevertheless, at least first of every 4 values should really decrease in course of relaxation. At any moment of relaxation, the Kontcar file contains the current structure as usually, but it also contains the most recent unstable direction here. And this is useful, for instance, when you need to continue your calculation, when you want to perform after the simulation was terminated and you want to do some fine relaxation, etc. So you can just take your Kontcar file and continue with the simulation. But if your relaxation was completed, so it's converged, yeah, so completed successfully, then you can use the Kontcar file, the resulting Kontcar file, to initialize another kind of simulations we are going to talk about shortly. That's intrinsic reaction coordinate calculations or following. All right, so after finishing the simulation for our demo reaction, I obtained the relaxed transition state. Here I compare it with my initial guess, and you see I was quite lucky. The final geometry doesn't differ much from my initial guess. There is very small reorientation of a molecule. Distance is shortened a little bit. Nevertheless, the energy decreased quite significantly by 3 electron volts. Okay, so once the transition state is determined, now it is important to identify potential energy minima corresponding to stable states linked with it. Okay, and this can be achieved by following intrinsic reaction coordinate, or IRC, which is defined as the steepest descent path from the transition state, and it's defined in mass-weighted Cartesian coordinates. For this purpose, VASP implements the algorithm of Hrachian and Schlegel, which I called DVV, or damped velocity Welle algorithm. That's because it uses velocity Welle algorithm to propagate positions and momenta in time. That's, by the way, that's an algorithm which is normally also used in molecular dynamics. The modification is that in this algorithm we are using variable time step, and it's damped version of algorithm. So after every step, we rescale velocities to have a constant value, V0, and this constant value should be provided by users. And the smaller value, the more accurate the calculation. Now, as mentioned, the algorithm uses variable time step. So for each time step, we decide if we rescale times previous time step, and the scaling factor is as follows. Here, delta 0 This is the tolerance factor defined by user via IRC delta 0. And delta n is estimated. And I will try to explain you how this is estimated. So suppose we are here at the structure Q in iteration n. Okay. And now imagine how we got there. 2 steps ago we were here, iteration n minus 1. Then we propagated using time step delta t n minus 1 and reach the geometry obtained in iteration n minus 1. Here we computed forces, decided on the new time step, which was like that, delta Tn, and then we eventually propagated to our current position. Now, having this knowledge now at this point, let's move back 2 steps ago, and let's check what geometry we would obtain if instead of moving by 2 small steps, we would just move by 1 big step, which would be sum of this and that step. Okay, the advantage here would be that we would skip 1 force evaluation, so we would save some computer time. So let's do that, and we just move on straight line, and we arrive at this prime Q, right? And now this distance between our current point and the point we would obtain in this way, this is a measure of accuracy. Okay, so the smaller this distance, the bigger steps we can actually take without compromising our accuracy significantly. So exactly this is this term. Now, as already mentioned, so a very well relaxed transition state is needed to initialize the calculations. If you used improved dimer method calculation, so unstable direction is already in the Kontcar file, you just copy Kontcar to Postcar and you can go. If you used Najid elastic method or some third-party optimization software, you need to go through the same steps to prepare the Postcar file, the same steps as when preparing the Postcar file for improved dimer method calculation. It's exactly the same kind of input. In the Incar file, we need to set Ibrion to 40 to tell the VASP that we wish to perform damp velocity Welle, DVV calculation. And now we need to set the flag IRC direction to either plus or minus 1. The thing is that the calculation consists of 2 independent steps, right? Starting from transition state, we can either move in direction that is parallel with initial, so with the unstable direction. In that case, we end up in this stable state, or we can move in direction that is anti-parallel to unstable direction. In that case, we end up in the other stable state, right? So we need to perform both calculations, and direction parallel or anti-parallel with the initial direction is controlled by RRC direction that can be plus or minus 1. Again, there are other flags that can be used to fine control the DVV algorithm. Normally, you don't have to touch them, but if you want, please check the documentation. Now, well, the post-processing of such calculation. First of all, the DVV calculation terminates when the energy starts to increase. Okay. Now, of course, we don't want to terminate any time when we have an increase in energy, because there could be just small fluctuation due to numerical noise. So user can specify how long the sequence of monotonous increase should be. That can be controlled by the flag IRC stop. The default value is 20. It's better shown on practical example. So what you see here is a typical profile for one branch of calculation. We started from transition state, so that's top of the barrier. So the energy initially monotonously decreased up to the point where we crossed minimum or some point close to it. And when we still push the system away from transition state, we then start increasing the potential energy. Okay, and if this happens 20 steps in a row, then the algorithm realizes that, yeah, now it's time to stop. Okay, so this is the termination criterion. Now the geometry, so imagine IRC stop is, you use default value, that's 20. So in that case, the 20th step from the end is our best approximation of the potential energy minimum. Normally, if you look at gradients, so normally close to the end of DVV simulation, the gradients are extremely low, typically much lower than you normally use as a relaxation criterion. But you should carefully check it. If needed, you should take that structure and find relax. And of course, in the end, to perform vibrational analysis to confirm that the state you have at hand is really potential energy minimum. Here I compare the relaxed reactant structure with relaxed transition state structure and compare the potential energies obtained in relaxation. So from that, I already see that the potential energy barrier, that's electronic contribution to free energy of activation, is as high as 0.99 EV. And we will see shortly that this will be the dominant contribution to activation free energy. Now, still about post-processing of DVV calculation, some useful output is written in the outcar file. In particular, what you can see here is the path taken in the calculation versus potential energy for that point. Okay, so this information can be easily accessed by simply grabbing the string IRCA. Now I perform my calculations in two branches, one for positive setting IRC direction +1, and the other for negative setting -1. So normally I run this in two different subdirectories, in this case P and M. Now for users' convenience, we use sign convention that when IRC direction is set to negative number, the path length is scaled by -1. So it's basically negative path length taken is written. And this is very convenient because then you can very easily plot profiles like this, where you can see how potential energy changed over a whole transformation, starting from reactant over transition state up to product. This can be achieved in 3 steps using bash commands. Here I extract potential energy of transition state. That's just energy of the first configuration generated. Next, I just grab exactly this string IRCA and extract third column, that's path taken, and fifth column, that's the potential energy. And that's my convention. I subtract from the potential energy the energy of transition state. I like to have transition state at 0. Okay. One more thing that I need to do is to sort by path taken, because remember, we start at transition state, but this profile should actually start from the end point of such a trajectory. So when these numbers are negative, when we sort it algebraically, so we revert the order at which energy versus path taken appears. So I store it in the file here. And then I do similar thing for the positive branch of calculation. This time I don't need to sort, it's already sorted. I just add this data to IRC shift, and here I visualize it, then it looks like that. Another useful thing is you can merge x.car files produced from 2 different branches of calculation, and then you can see what motions individual atoms underwent during the transformation. So you can produce movies like that showing whole transformation path. Now here the post-processing is a little bit more complicated. So we prepared some tools with which you can manage that. And by the way, all these Python scripts, which I'm mentioning in my talks, will be available for you on hands-on session. Now, once we have obtained relaxed geometries and corresponding potential energies and harmonic vibrational frequencies for reactant and transition state, now we are at position to perform thermodynamic calculations. Okay, so to this end, we will always use this defining equation for free energy. And we just need to express partition function for different degrees of freedom using adequate model. For electronic degrees of freedom, partition function can be expressed like that. G0, that's electronic degeneracy. For extended systems, you should take spin degeneracy into account. So that would be 1 for singlet state, 2 for doublet, 3 for triplet, and etc. And U of Q0, that's nothing but the energy of relaxed state, mu, reactant or product or transition state. Okay, so plugging this equation into this formula, you obtain free energy, electronic contribution to free energy. And in the special case of singlet state, G is 1, logarithm of 1 is 0. So then you recover this trivial identity. in the special case of singlet state. For vibrational degrees of freedom, as already mentioned, we use harmonic oscillator model. The quantum mechanical expression for the partition function is like that. Here the product is through all vibrational degrees of freedom. For extended systems, this should be 3 and minus 3 vibrational degrees of freedom, because remaining 3 degrees of freedom are translational. If you have molecule, you should have 3 and minus 6 vibrational degrees of freedom if it is stable state. Again, inserting this formula here, then you obtain a result for a vibrational free energy. This is in principle all that is needed when your reactant and transition state, or all relevant states, are extended systems, periodic systems. If, however, your system is molecular in gas phase, you need to take into account also rotational and translational degrees of freedom. For rotations, rigid rotor approximation is used. The partition function now depends whether you have linear or non-linear geometry of molecules. So let's discuss non-linear case. Here, sigma, that's the symmetry index, okay, which is just the order of rotational subgroup of the system. And I, 1, 2, and 3, these are momenta of inertia and can be obtained as eigenvalues. This is wrong, eigenvalues of inertia tensor. This is 3 by 3 matrix. And this is computed using the structure of your relaxed reactant or transition state. Okay, so this only depends on geometry and atomic masses of your state. In the case of linear molecule, if you diagonalize such matrix, you would have 1, 0 eigenvalue, and 2 eigenvalues would be identical. So that's why you have only I1 here. In the case of translational degrees of freedom, we use ideal gas model to represent these degrees of freedom. The partition function takes very simple form, because for the given conditions specified by volume and temperature, so the only extra thing that we need is the total mass of molecule. Okay, so this is very easy to compute. So both rotational and translational free energy contributions are easy to compute. They don't require any ab initio calculations. You just take geometries and masses and you have it. Okay, so here are results for our demo reaction. So in our case, all relevant electronic states were singlet. So electronic free energy was directly equal to potential energies of relaxed reactant and transition state. And from the difference between these two, I can see that this is my electronic energy contribution to activation energy. It's periodic system, so we don't have to consider any rotational and translational degrees of freedom, only vibrations. There are 3 and minus 3 real frequencies for the reactant, and 3 and minus 4 real frequencies for transition state. And here is the contribution of vibrational degrees of freedom to activation free energy. So we see that it's significantly smaller compared to electronic degrees, but it's not negligible. And when we sum up these terms together, so then we obtain our static approach result for activation free energy. And this is the value to be compared with the result that we obtained using molecular dynamics in the next lecture. Okay, so for the thermodynamic calculations, we need vibrational spectrum with correct number of vanishing and imaginary frequencies, right? Due to numerical artifacts, it could happen that the correctness of vibrational spectrum is difficult to assess. Let me give you an example. This is my transition state candidate for another reaction, that's gas phase alcohol isomerization. I had hoped that this was very well relaxed, because I used my usual stringent relaxation criterion. Nevertheless, when I performed vibration analysis and look at lowest 8 vibrational frequencies, I saw that, yeah, first of all, I didn't see any vanishing frequencies, and second, I saw here 4 imaginary frequencies, right? So evidently, I could not use this data in thermodynamic calculations, so I would have to do something about that. First of all, the problem with vanishing frequencies can be eliminated by transforming the Hesse matrix using frequency calculations. in an auxiliary set of translationally and rotationally invariant internal coordinates, chi, and then back into Cartesian coordinates. Okay, so this can be achieved by this kind of transformation where A is a Moore-Penrose pseudo-inverse of Wilson's B matrix. That's basically, this is element of such matrix. This is basically Jacobi matrix for transformation between internal and Cartesian coordinates. So now in vibrational calculations, we can replace the original Hesse matrix by this transform one. This idea is implemented in VIPFRAC program, which is also available for you on hands-on session. And indeed, when we do that, so we now see that our vibrational spectrum cleaned up. We can now clearly identify the 6 vanishing frequencies. It's a molecular case, so indeed there should be 6 frequencies, vanishing frequencies corresponding to rotations and translations. Still, its transition state candidate, it should have only one imaginary frequency, but there are 2. So still there is one extra imaginary frequency, and we should do something about that before computing thermodynamic contributions. Now, if you look into literature, this problem is sometimes solved by discarding all frequencies below certain threshold. Typically, this threshold is chosen to be something between 25 or 100 reciprocal centimeters. In my humble opinion, this is not a good idea. And the reason is that, of course, the lower the frequency, actually the higher the corresponding vibrational free energy contribution. So by using this strategy, we are actually cutting the most important contributors to vibrational free energy. Moreover, the number of modes that we cut in this way for reactant and transition state is not necessarily identical. And also the nature of modes that we are eliminating based on simple threshold, frequency threshold. So even nature of such mode is not necessarily similar, right? So that's why we cannot simply expect a systematic error cancellation when you use this kind of strategy. We can do better. There is a simple systematic strategy which we can apply to eliminate the problem with residual imaginary frequencies. And I would like to show you what I do in my research. So inspecting the file Hesse modes Molden, I can simply check the vibrational modes for both imaginary frequencies or negative force constants that I have. Now, comparing with the reaction itself, so I see in my reaction what should happen is actually the methyl shift and water reconnection. So now when I look at my vibrational mode, so I see that the mode with a larger negative force constant pretty well corresponds to this kind of motion, whereas the other vibrational mode is just some soft delocalized mode, pretty much involving all atoms, and there is some weird rocking of water molecule, right? So this certainly has nothing to do with reaction of my interest. So this is the mode which I would like to eliminate. Okay, I would like to stabilize the system along this mode. So a straightforward solution to the problem, of course, is then to scan the energy along this problematic eigenvector. Okay, I scan energy in a series of single point calculations and then identify the minimum, fine relax if needed, and recompute vibrational spectrum. Okay, and this can be done very easily. So from Hesse modes, we just take the corresponding eigenvectors. So in our case, the problematic one was the one with lower negative force constant. So this is n line, and we store it in separate file. Let's call it mode dot. Then we need to extract the information that allows us to construct POSCAR. So we take a header from the POSCAR file. So we take first 7 lines, and we add keyword Cartesian because we are going to work with Cartesian coordinates. We also need Cartesian coordinates for unperturbed system, and we can extract those from outcar file generated by vibrational analysis performed in the previous step. Okay, so this is the script I'm using to a series of bash commands I'm using to extract this information, but you can also copy paste this by hand from the outcar file from the table where positions and forces are listed. Okay, and I store my Cartesian coordinates in the file called x0 dot. Okay. And then I simply perform simple sequence of bash commands. Here I have loop over displacements over their size and direction. I recommend to use some small displacement. So my values are range between minus 0.2 and 0.2. Then I will construct the postcard file for the perturbed structure. So here I basically add mode scaled by displacement value, okay, and add it to non-perturbed Cartesian coordinates and construct postcard file in that way. Then I perform single point calculation for VASP, so using VASP, and extract energy and print energy versus displacement and store it in the file energies. When I visualize that file for my particular case, I see profile like that. And now we see that indeed for the unperturbed structure, so delta 0, okay, so this is not a minimum along the surge line as it should be. And indeed, we can stabilize the system by performing negative displacement, the displacement in negative direction. So what I did, next step was I just took the structure that was closest to minimum, fine relaxed, perform vibrational analysis, and post-process it, and I saw that my spectrum cleaned up. I had only one imaginary frequency and 6 non-vanishing frequencies. This is exactly how the spectrum for well-relaxed molecular transition state should look like. One more thing I would like to address is importance of quantum mechanical effects in vibrational thermodynamics calculation. So you might have noticed that when we discussed vibrational contributions to free energy, we used quantum mechanical expression for partition function. Nevertheless, in molecular dynamics, we will discuss in my next lecture, we generate semi-classical ensembles. Okay, so for fair comparison between molecular dynamics and static approaches, it would be useful to formulate or to use also strictly semi-classical static approach, right? So that's why it could be useful to replace quantum mechanical expression for partition function by its semi-classical counterpart, and you can easily derive this equation from this equation by assuming that exponents here are small numbers, much smaller than 1. In that case, you can Taylor expand them and cut after the linear term, and you arrive exactly at this formula. So with that, and so plugging this into defining equation for free energy, we find this expression. So once again, we can determine vibrational free energy as sum of contributions, independent contributions from different vibrational frequencies, just like in quantum mechanical case, of course. Now, how important the quantum mechanics, the nuclear quantum effects are in a free energy calculation. So first of all, yeah, so to test that, here I plot the difference between quantum mechanical and semi-classical vibrational energy computed for reactant and transition state for different temperatures. And as you can see that at every temperature, the difference is quite large. Even at 1000 K, it's as large as 0.5 EV. That's a lot. On the other hand, this difference looks pretty similar for both reactant and transition state. So there will be certainly quite large cancellation when we plug a reactant and transition state free energy into activation free energy formula. Indeed, when we compare activation free energies computed using both variants, we see that this difference is very, very small already at low temperature. At our temperature of interest, 440 K, this difference is only 0.012 milli EV. Okay, so this result means that for our reaction, for this particular reaction and under these particular conditions, okay, so the use of semi-classical approximation is satisfied. So it's justified, and we can reasonably well compare such results with molecular dynamics results. And it also makes sense to use molecular dynamics for this kind of reaction. One more thing you might wonder, the formula that we used to compute activation free energy using static approach was the simple one. It was just free energy difference between transition state and reactant. Whereas at the beginning of my talk, we arrive at a bit more complicated general formula. Now you might wonder, but whether these two expressions are compatible. In other words, starting from more general formula and implementing assumptions made in the static approach, can we indeed arrive at this form as we should? Okay, so I don't have much time. I can only outline the proof here, but yeah, the answer of course is that yes, these two formulas are compatible. Let me briefly to go through that, at least to give you idea how proof goes. So first assumption that we make use of is that reaction coordinate can be approximated by eigenvector of dynamical matrix, so by vibrational mode with frequency omega psi. Okay, so then we can express a reversible work. This is the first term that we have in general formula. Formally, this is free energy difference between a state psi asterisk, that's transition state, minus free energy of state of reference reaction state, right? So remember, both these terms are computed for fixed value of psi. Okay, so the reaction coordinate should not contribute to any of those terms. So this is fulfilled, this condition is fulfilled for transition state. So this is indeed exactly the same thing, because you remember, in static approach, the unstable vector was linked with imaginary vibrational frequency, which is not included in thermodynamic calculation. So indeed what we have is constrained transition state in sense. But for reactant, we have all vibrational degrees of freedom included in thermodynamic calculations, but since the reaction coordinate is pure eigenmode, so we can easily identify its contribution to reactant's free energy and subtract it. Okay, so this term can be very easily expressed like that. Okay, so now let's take a look at this logarithmic term, and so in particular at velocity and at probability density. This is a bit more complicated, so I will only tell you so what I did. So I used general expression for an observable in canonical ensemble, the one we introduced at the very beginning of my talk. Then I changed coordinates from Cartesian to normal coordinates. Okay, and with that, it's fairly easy to determine average velocity for the normal mode, so one of those coordinates. And that's here it is expression I got. So as you see, it's something that depends only on temperature, but not on identity of that vibrational mode. Following the same steps, one can compute also probability density, again, using general expression for observable. And what I got is Gaussian function. Now we can choose a reference reactant state arbitrarily. So you remember one of the assumptions in a static approach was that it's the potential energy minimum that is representative of whole reactant state. So that's a natural choice for a reference reactant state. If we choose it, so this formula simplifies to this simple form where we have vibrational frequency of this unstable mode, so to say. Okay, now combining these two pieces of information in logarithmic term, we, after very simple manipulation, again obtain vibrational energy contribution coming from reaction coordinate. Okay, and now combining all those pieces together, right? This is reversible work, violet. So this is this logarithmic term. So we see that, you know, this term which we subtracted here is added here. So in the end, we indeed arrive at the same simple expression as used in the static approach. And in the final part of this talk, let me briefly discuss limitations of static approach. The potential energy surfaces of all but simple systems are complex. So they usually have many local minima and many local saddle points, usually corresponding to just different orientations of reactant molecules, maybe with respect to substrate or with respect to each other. Of course, in such cases, any single stationary state obtained in relaxation cannot serve as a meaningful relaxation of entire state, making the basic assumption of static approach rather questionable, right? Let me give you an example what kind of problems this could cause. This is an example from our research, where we investigated mechanism for type B alkene isomerization of C7 species. In that study, we used molecular dynamics as generator of initial structures for relaxations of transition state, and then we used IRC calculations to find corresponding stable states. Now, we found that although individual configurations that we identified in this way had very similar internal geometries, there was surprisingly large variation in potential energies and free energies of relaxed reactant and transition state. Take these two structures as example. So these are two transition state configurations. So this is basically the same internal structure, just the whole molecule is rotated differently inside zeolite. So this is normally supposed to be soft, so this internal rotation in empty space, it's normally supposed to be a soft degree of freedom. Nevertheless, the difference between these two structures is as large as 40 kilojoules per mole. Now, combining the data from reactant and transition state, we found that static approach is basically useless for this in this case because it leads to prediction of activation free energy that could be anything between 50 and 90 kilojoules per mole. So this is simply intolerable variance in results. And the things could be even worse because the temperature can induce topological changes on free energy surface such that the resulting free energy surface is very different from the underlying potential energy surface, which we analyze in the static approach, right? So in such case, not only individual stationary points, but are no longer reasonable representations of stable and transition states, but also whole mechanisms that we determine in static approach could be wrong. Let me give you again example from our previous research, where we investigated mechanisms of alkane dehydrogenation catalyzed by acid zeolite at 800 K. And we studied this mechanism by uncompromised simulation method. It is called transition path sampling, which is really designed for investigating mechanisms at finite temperature without any pre-assumptions. Now, in static approach, so this is our reactant, this propane interacting with zeolite or acid site in zeolite. So in static approach, the product that is obtained looks like that. This is alkoxy species. Okay, where the hydrogen molecule is created and the rest, the cation, is attached to zeolite framework. Now, at finite temperature, so at this high temperature, 800 K, so the carbenium cation that is unstable, but it is created as unstable intermediate. It's partially stabilized by entropy, okay, at high temperature, and it lends it some time to rearrange into some of its more stable forms, for instance, secondary or cyclic cation. And this is exactly the mechanism how entropy opens up new reaction routes, leading to very different products, okay? So obviously, to get rid of these limitations, so we have to go beyond static approach and its simple models. So ideally, we should perform explicit sampling of potential energy hypersurface using Monte Carlo or molecular dynamics, right? So how to do with molecular dynamics, how to compute free energy of activation using that technique. So this is exactly the topic of my next talk. Okay, so this is the end of my talk. Thank you very much for attention.
Thank you very much for the lecture, Thomas. It was very interesting. We're going to take a short 10 to 15 minute break, and then we'll start another session with the Q&As.